Hello, in this video I'm going to talk about what in quadratic theory we call the discriminant. In general, we know that a quadratic equation takes the form of ax squared plus bx plus c, and of course all of that is set to equal 0. We also know that the quadratic formula is minus b plus minus the roots of b squared minus 4ac, all of that over 2a. Now what's really interesting, and one could say, I suppose, that there's a deep connection between the solution from quadratic formula and the graph of the parabola, namely that you can tell how many real solutions you're going to have from the value inside the square root. And this is something I believe I might have highlighted in my video on a proof of the quadratic formula, that the discriminant is part of the quadratic formula under the square root. It's this right here that I'm highlighting in red. B squared minus 4ac. That is the discriminant. And the reason it is called the discriminant, or we could say that the argument of the square root being the expression b squared minus 4ac, the reason this is called the discriminant is because by using its value you can discriminate the various solution types of the given equation, and so in that sense the discriminant can be positive, negative, or 0, and this determines basically how many solutions there are to the given equation. So for example, if b squared minus 4ac is positive, this indicates that there will be two distinct real solutions, distinct real solutions. If b squared minus 4ac is negative, this indicates that there will be no real solutions or roots, no real solutions. I will save a video on complex or imaginary roots for the future, but in this case we know that if b squared minus 4ac is negative, there are no real solutions. If b squared minus 4ac is 0, well, interestingly, this indicates that there are two equal roots. Another way to phrase this would be to say that there's just one repeated solution. And so to offer some context to what all of this means here, let's just consider an example. Say we're given, I don't know, just start really simple. Say we're given y equals x squared plus 3x plus 2. 3x plus 2. Well, and using the discriminant, well, actually, before we get there, we know that this is a. A is 1, right? There's a 1 in front of the x squared term. It's implicit, so a is 1, and it's positive. B is 3, and c is 2. So in using the discriminant, b squared minus 4ac, we can quickly discern what solution types there are with respect to this given equation. And so b squared, that's going to be 3 squared minus 4 times a, which is 1, times c, which is 2. 3 squared, of course, is 9, minus 4 times 1 is minus 4, times 2 is minus 8. So the discriminant is going to equal 1. And it's positive, which immediately tells us that there are two distinct real solutions. And this is the value of the discriminant, and why it's very useful is that we can very, very quickly discern what solution types there are with respect to the given equation in relation to its graph. And But actually, interestingly, there's another way to think about the discriminant, which might prove useful. If we bracket what we found here, and maybe I'll just box it off to highlight it. If we bracket what we found here and return to it in a moment, let's consider a slightly different approach to the discriminant. And for example, well, actually, before we get there, there's something I have to preface what follows by understanding or by highlighting that we know that when a is greater than 0, the curve of the parabola, the curve is going to be upward facing. It's going to be an upward facing parabola, right? Oops, and I accidentally drew a U. Upward facing parabola. If a is less than 0, the shape, the curve, I'll just write the curve is going to be a downward facing parabola. And the reason I preface what follows with that statement is just because it's important to remember this, because now when we turn to a slightly different approach to thinking about the discriminant, what it turns out is that we can check the general shape of the curve by considering the discriminant, particularly when specific conditions apply. And when those conditions apply, the general shape of the curve will take the following form. And so if, in this case, for example, to start, if b squared is greater, and I'll just write the discriminant again, b squared minus 4ac. If b squared is greater than 4ac, what this tells us, and actually I should write, and a is greater than 0, well, when a is greater than 0, we know it's going to be an upward facing parabola, right? So in that case, like if we look again at a general, or I'll just rewrite it, ax squared plus bx plus c equals 0. When a is greater than 0, which means it's positive, so 1, 3, 10, 50, whatever, we know immediately we have an upward facing parabola. If a is negative, therefore, in other words, if a is less than 0, so negative 1, negative 10, negative 100, whatever, we know it's going to be a downward facing parabola. So in this example, if when b squared is greater than 4ac and a is greater than 0, the graph is going to look like this. We have the x-axis, we have the y-axis, and we're going to have two distinct real roots or solutions. It's going to look something like that. So two distinct real roots or solutions. So when b squared is greater than 4ac, two distinct real solutions. Which is interesting when we think about the statement above, right here, if b squared minus 4ac is positive, two distinct real solutions. Now, if b squared is equal to 4ac and a is still greater than 0, it turns out that we are going to have a graph that has that looks like this. If this is the x-axis and this is the y-axis, and this is the origin, of course, right? I don't know if I need to make that explicit. The graph is going to look something like this. It's going to come down and it's just going to touch, you could say kiss, or even at a tangent, the x-axis. It doesn't cross the x-axis, it just kisses it basically. And so in this case we're going to have two equal roots. And so if you compare that to the statement above, if b squared minus 4ac is 0, two equal roots. There's just another way of thinking about it. Wherein in this case, if we have b squared, and in another case, if we have b squared is less than 4ac, and a is still greater than 0, we know it's still going to be an upward facing parabola. But it turns out that if b squared is less than 4ac, this is the x-axis, and this is the y-axis, our graph is going to look like this. And there will be no real solutions. It will look something like that. No real solutions. Likewise, we could expand on this actually. So in considering the example on the left hand side here, if b squared is greater than 4ac, but in this case a is less than 0, well, we know as previously discussed and when a is less than 0, the curve is going to be a downward facing parabola. So when b squared is greater than 4ac, but a is less than 0, we're still going to have two real distinct solutions, but the graph is going to look something like that. Right, and that's the origin, of course. When b squared is equal to 4ac, and a in this case is still less than 0, well, just like the graph directly above, we're going to have one repeated solution, except it's going to be downward facing parabola. So it's going to look, this is the x-axis, this is the y-axis, it will look something like that. Again, just at a tangent to the x-axis, really. It will look something like that. And so again, there are two equal roots, or one repeated solution, however you want to phrase it. And now if b squared is less than 4ac, just like the example above, but a is in this case less than 0, instead of a being greater than 0, the graph is going to look, this is the x-axis, y-axis, it's going to look something like this, and in this case again there will be no real solutions. So it's quite interesting. It's just a different way of thinking about the discriminant, I suppose. And in short, and the lesson is the same in that we can use the discriminant to establish when a quadratic equation has equal roots, real roots, or no real roots. And so equal roots is when b squared equals 4ac. Real roots is when b squared is greater than 4ac. And no real roots is when b squared is less than 4ac. And now actually, to use an example to kind of put all of this into practice, let's return to the previous equation. If I copy and paste this, if that's possible, copy and paste it down here. Okay, that looks alright. I can just fix what was cut off, which is x squared, and this is of course b squared minus 4ac, 4ac. Right, so this is what we previously found. We found, just by using the discriminant very, very quickly, that this equation has two real distinct roots. But let's go through all of the steps and sketch this graph and see if that was indeed correct, as it should be. So immediately, actually, I'll rewrite it, just for the sake of keeping things neat and tidy. So we have x squared plus 3x plus 2. We know to start that a is 1, b is 3, c is 2, and we can discern immediately, very quickly, that a is 1 and it's positive. So therefore a is greater than 0, which is to say that the shape of the graph we immediately know is going to be an upward facing parabola. Next, when y equals 0, we know that we can set this equation. It's basically the same as we're setting the equation to equal 0. So it's going to be x squared plus 3x plus 2. And now we can solve this by using the quadratic formula. We could complete the square, or it's very, very simple. We could just factor it. And so it actually serves as a decent point of revision, where we want to find AC, A times C, so that's 1 times 2, so AC is 2. Now we want to find what multiplies to 2 and adds to B, which is 3. Well, 1 times 2 clearly is 2, and 1 plus 2 is 3, so 1 and 2 are our factors, and so what we can do is rewrite this as x squared plus x plus 2x plus 2, and now we can factor out an x from the first pair of terms, and so that's going to leave us x times x plus 1, and we can factor out a 2, so that's going to be x plus 1, and so therefore we are left with x plus 1 and or I should say x plus 2, and therefore our two solutions are x equals negative 1, and I will box that off, and x equals negative 2. I will box that off. Okay, so now we have our two roots, our two solutions, and the coordinates on the graph will be -1 and 0, and -2 and 0, and again that's where the graph will cross or intersect the x-axis. And now to find the y-intercept, actually I'll just erase this quickly, save some space. To find the y-intercept, we just set x equals 0, and so when x is 0, y is going to be 2. And that is because if x squared is 0 plus 3, and 3 times 0 is 0, you're just going to be left with 2. So y equals 2, so we know the y-intercept is 2. Now, in using the discriminant, let's use it slightly differently than we did above. And in this case, we know that b squared, so I'll just rewrite it actually, b squared minus 4ac. We know b squared is 3, right? B is 3, so that's 3 squared, that's 9. So b squared is 9, so I'll just write b squared equals 9, and 4ac equals, well, 4 times 1 is 4, times 2 is 8, right? And so b squared, we can quickly deduce, or we can discern that b squared is greater than 8. So b squared is greater than 4ac. B squared is greater, therefore, than 4ac. And when b squared is greater than 4ac, we know that we are going to have two distinct real solutions. And when a is greater than 0, such as in this case, we know it's upward facing, as we already discerned. And so therefore, in using the discriminant, we found that there are two distinct real solutions, which certainly validates what we had found when we solved this equation and we found its two solutions. And so I can just quickly graph this. Actually, it's going to be on the negative x-axis, so it will be something like that, where this is x and this is y, and this is 1, 2, 3, so -3, -2, -1, this is 1 and 2. And so we know that there's going to be a solution at x equals -1, so right there, and x equals -2, so right there. And so the graph, the parabola is going to look something like that. It's not the neatest sketch, but it will do. And so, yeah, what's interesting again is that you can use the discriminant in two ways. You can just find what b squared is, so that would be 9, because it's 3 squared, and then what 4ac is, and then you can, if b squared is greater than 4ac in this case, then we know that there's going to be two real solutions. Or you can just use the discriminant, work with the discriminant in the way I did at the very outset, which is maybe a little bit easier, is where if you just basically solve the discriminant b squared minus 4ac, which is 3 squared minus 4 times 1 times 2, which comes down to 9 minus 8, which is 1, so we know it's positive, and when the discriminant is positive, we know that we have two distinct real solutions.